All right, so today we're doing things a little bit differently. This is not from our textbook, but I wanted to go over what's known as the geometric interpretation for least squares regression. Okay, and this applies to multiple linear regression. Okay, so this is the geometric interpretation of least squares regression. Okay, and this applies to both simple linear regression and multiple linear regression. So this is how I teach Stats 10. I write on the board like this, but this class is not as conducive for this kind of format. But okay, so let's try this out. Okay, so we're going to I'm going to start off with the most simple case of least squares regression. Okay, and because so just let's say we have two values of y. Okay, so y will be is going to be a vector, and the two values of y we'll say are 2 and -1. Okay, and we are going to fit a so just remember things in vector notation or matrix notation. We're going to have y equal to x beta. Yeah, I'll post these, okay? And I'm also videotaping it, okay? X beta plus our error term, okay? And in our case, we are just going to fit, because we only have two values here, we're going to just fit a single, a constant to this, okay? So our x term is just going to be 1 and 1. Okay, so just stepping back, and then we want to find beta hat to minimize our squared residuals. Okay, so just this is completely silly. So if we were to plot our data, okay, it really doesn't matter, okay, and we have let's say we have y at 2, so I'm going to just put a dot right here, and y at -1, okay, right here at -1. We're trying to fit some constant value, okay, such that it minimizes. So I'm going to have like some potential fits here. Okay, we want to pick the beta, so these are all at location beta hat. We want to pick the beta hat so that the squared residuals are minimized. Okay, so what is the value we're going to pick here? Yeah, halfway through, right? So it's going to be right here where beta hat is equal to 0.5. Okay, so this is very easy to see visually. Okay, but so this is y, and this is x or whatever we want to have. Okay, but we're going to do this in n-dimensional space now. Okay, so because we only have 2 data points, our n is 2. Okay, so I'm going to show you least squares regression in n-dimensional space. And also, because I'm drawing on a 2D plane, I'll do this example again just at a higher dimension, but I'm limited in how many dimensions I can show on a screen, which will be 3. So n-dimensional space here, okay? So I have 2 points. So we are in 2D space. Okay, so here this axis represents y1, and this axis represents y2. Okay, and so we are at the point 2, 1, 2, and -1. Okay, and so this, I'm going to do my very best to draw a straight line right here. So this is a vector. This vector is, we can call it A or whatever. This represents the vector from the origin to the location of our data. Okay, so this, I don't know, so this vector represents location of our data. Can you guys read that? Okay. We are limited. Let me save this to. This is Stats 101A, and it is October 30th. Can you believe that? Okay. Because our x is in the space 1, 1, okay, this represents this. Trying to draw a straight line as much as possible. This one represents our, and I'm going to, so this represents a unit vector in the space of x. Okay, so this is our unit vector x. All right, and so x, what beta does, beta in our case, because we're just trying to fit one term, I should say beta is just going to be a scalar, okay? Is just as a scalar, okay? Because we're only fitting one x term, okay? So only one quote-unquote x term to fit. So all we can do is kind of just move along in this direction, or in this direction here. Okay? And what we're trying to do is we're trying to find the location in our, basically on our x vector here, that minimizes the distance to our data point. Okay, and so visually that means we're going to have a right angle between the location of our data and where we're located on here. Okay, does that kind of make sense? So we're projecting. We're projecting the vector representing our data onto the onto our x vector. is what we're trying to do. Okay. So our x vector, it's a vector because we're only in basically in 1D space here. Okay. So we're trying to project this. So how do we figure out this location? Okay. Well, this distance here, okay, this red distance, what is this? This is our E. This is our E, okay? Because, well, let me see if I can find another color here, all right? This right here, this is the projection. This vector right here is our projection xb, okay? This location is xb, okay? This is our data y, and so this red vector is the this is our E here. Okay, I don't know, can you guys see that? All right, and so we want to what is the value of E? We can figure out the value of E. All right, and this is just from Pythagoras's rule. Okay, we could say, you know, it's going to be this squared plus this squared is equal to this squared, right? So E squared is equal to basically y1 minus x beta hat squared plus this is going to be y2 minus x beta hat squared. Okay. All right, and so, well, our x's are 1s, so I can just reduce this to y1 minus beta hat squared plus y2 minus beta hat squared, right? Okay, and so to minimize our squared residual, let me, I'm going to flip to the next slide. Is that okay? So to minimize the squared residual, we're going to just take the derivative of this, set it equal to 0, and find where what value of b equals 0. So I leave off with e squared equal to, yeah, so you don't have to write this down again. Okay, so we take the derivative with respect to beta hat, okay, to find the beta hat that will minimize this. All right, and so we get negative 2 y1 minus beta hat plus over here I get negative 2 y2 minus beta hat equal to 0. Okay, and so solving for beta hat, we get negative 2 y1 plus 2 beta. Well, I should just divide everything by 2, and I'll have y1 plus y2 minus 2 beta hat equal to 0. So I get beta hat equal to y1 plus y2 over 2. Okay, and this is exactly what we were expecting, right? So this tells us that the beta hat should be equal to 2 plus a negative 1 over 2. So this we get 1/2. Okay, and so this is the scalar that we would use. So we would have y equal to x beta plus error. So now we have 2 minus 1 equal to x, which is 1 times 1/2 plus the error, which we can solve for or figure this out. This is just going to be the difference here. Okay, so this is just a very simple case where we're fitting basically one-dimensional data, two data points, okay, in two-dimensional space, and we're projecting it onto our x vector here. Okay, so I'm going to generalize this to, I guess, a three-dimensional case where we have three data points and two variables, and we'll see the same kind of process, and then that can then be generalized to n-dimensional space. But we can't visualize n-dimensional space. Anything higher than 3D we can't do. So the most I can represent in this form is 3 data points. Okay, but if you have 50 data points, you would have 50-dimensional space. You have a vector representing in 50-dimensional space representing your data. Okay, so imagine, so this is imagine we have 3 data points. We have 1, 1, -1, -1, and 3, 2. Okay, and so this could be like a simple linear regression model. So in regular xy, in xy space, we have a data point at -1, -1, 1, 1, and then 1, 2, 3 right here. Okay, and we're trying to fit the what line fits this best. This is what we're trying to do. Okay. All right, so I'm going to try to draw this in three-dimensional space. I'm going to do a terrible job here, so forgive me, please. Okay, so let's we have the vector of our y's, which will be y1, y2, y3, which is 1, -1, 2. Okay, and then the model that we're going to fit is y equal to x beta plus error. Our x, what does our x thing look like? Okay, so we have we're fitting 2 terms here. Okay, so so our x will have 1, 1. So yeah, so I got 1, 1, 1, and then basically this would be x. So here, let me back up. Okay, so I've got x sub 0, 1, x sub 0, 2, x sub 0, 3. All right, or would it be 1, 0? I always, maybe it's the other way around. Sorry. 1, 0, x 2, 0, x 3, 0, and then I've got x 1, 1, x 2, 1, and x 3, 1. So in this case, this would be 1, 1, 1, and 1 -1 and 3. Okay, and our beta is going to be our basically beta 0 and beta 1. Okay, so we're in matrix notation, right? So we get we fit it like this, and then we would have a epsilon term that would be epsilon 1, epsilon 2, and epsilon 3 are residuals. Okay. All right, so I'm going to draw our y vector, or our data, our y vector in three-dimensional space. I'm trying. This is going to be hard for me to do. So I've got this, and this, and then how am I doing this? Okay. So I just have to label one of these. So I don't know, this might be dimension 1, dimension 2, dimension 3. So I'm up here, and I'm going out into -1, and then and I'm going out to 2. So carrying this all the way out, so I'm trying to draw a little rectangular prism here, and okay, so this here represents from the origin to this point. I can draw a straight line. This is the spot 1, -1, 2. I hope that's right. Okay. All right, and then so now, okay, how does this work? No, I hope I do this correctly. So I'm going to just look at this one, okay? 1, -1, and 3. So what is that? 1, -1, and I'm coming out, oh, this is like the worst. Basically, I'm coming out to here. So this is this will be this over here. Oh, look at that. I actually made it there, okay? So this is in this space, and then over here I'm going to represent this in this vector. So this, so basically 1, -1, and 3 will be in blue, and 1, 1, 1 will be in red. So that would be, oh dear, that's like it's like right over the origin, huh? When I project it here. Oh no, maybe it's okay. So I got one spot right here. Okay, and then so now two vectors define a plane, right? Okay, so imagine these two defining a plane upon which we can project this purple thing. Okay, so what does this plane look like? It's kind of, oh man, I can't. It's like going the coming at you. Okay, so I'm gonna have to. I don't know what the plane looks like. So something like this. Okay, it doesn't. It's just terrible. There's no hope. Okay, and we are trying to project this purple vector onto the plane defined by 1, 1, 1 and 1, -1 and 3. Okay, so this is like it's hard to see, but I don't know how to do it. What will this be? Okay, so imagine let's say it comes down to here. I have no idea. We are going to get I just made this up. I have no idea if this is even remotely geometrically accurate. Okay, it's probably not. It's completely wrong. I'm sure of it. Okay, so we're projecting this thing onto said plane. Okay. All right. So what we have now is that the location here, and so our epsilon term, okay, is going to be the difference between basically y minus our x beta hat, okay? So basically, let's our x beta hat is going to be beta hat 0 plus beta 1 x1, which will just be 1. And then we got beta hat 0, and then it'll be minus beta hat 1. And then I've got beta hat 0 plus 3 beta hat 1. Okay, so I'm just multiplying my x by my beta term, and I get this. Okay, and then so what we have here is we're going to try to minimize our squared residuals. Okay, so this is going to be y1 minus the quantity beta 0 hat plus beta 1 hat squared plus y2 minus and our third term is y3 minus I think I did that correctly. Okay, so we're just minimizing the difference between each y excuse me, and our x beta hats. Okay, our y hats essentially. Okay, and so we're gonna take the partial derivatives with respect to beta 0 and with respect to beta 1, I guess beta 0 hat and beta 1 hat. Okay, so I did this earlier, and I hope I did this right. I'm pretty sure I did. So I'm just gonna jump. So if you take this, you know, I'm gonna skip the work, and you're gonna get 6 beta hat 0 plus 6 beta hat 1 minus 4 equal to 0. And then if you take it with respect to beta hat 1, you get 6 beta hat 0 plus 22 beta hat 1 minus 16 equal to 0. Okay, and then so now we have 2 equations and 2 unknowns, and we're going to solve for beta hat 1 and beta hat 2. And so what do we have? We get, so I'm going to do this thing minus this thing, right? So I do 6 minus 6 beta and 6, so I get negative 16 beta hat 1, negative 4 minus 16 plus 12 equal to 0. So that gives me beta hat 1 equal to 12 over 16 equal to 0.75. And then plugging this back into here, I think I get beta hat 0. Let me just verify and make sure I'm not lying to you. So over here I would have basically 6 beta hat 0 plus 6 times 0.75, which is 4.5 minus 4 equal to 0. So I get beta hat 0 equal to minus 0.5 over 6, or minus 1/12. Is that what I got? Okay, good. So that is, these are my least squares estimates. Okay. All right, and so we can verify this in R, and we can say so I can say x is equal to, what was x? X is 1 minus 1 and 3, and y is 1 minus 1 and 2. Okay, and then so we can fit, we can just ask summary of our linear model where y is explained by x, and here, let me just do that again. Okay, and indeed we get what we expected. We got an intercept of -1/12 and a slope of 3/4, 0.75. Okay, and this is our residual vector. So this would be our error term, which is our error term. What is it again? 0.33. So 1/3 and -1/6, -1/6. So I got 1/3 minus 1/6 minus 1/6. So if I had drawn this correctly, the actual projection would be of the form this thing, this green line here would be this thing, okay? But this is our residual term. But that's it's hard to visualize in this. But so basically, you know, we can generalize this to n-dimensional space where you have a vector. Your y vector represents all of your y data in n-dimensional space, and then you have your x vectors representing the you know, however many predictors you have. So if you have 50 data points and you have 3 predictors, okay, then you'd have three vectors representing the space in which you can fit your data. So you'd have I guess a 3-dimensional space, and then you are going to project your 50-dimensional data vector onto the 3-dimensional space, which we cannot visualize really in our head. But essentially, that projection that you are trying to do, the point where it reaches the space that you have, your P space. So if you have P predictors, that P space, that is going to be your fitted values, okay? And then the distance between the P space that you have and the y vector in n space will be a residual, also in n space, okay, showing the distance there. Does that make sense? I feel like, you know, I feel like I can't draw any more here, but but the least squares thing is you're projecting the your data vector into the prediction space that you have, the space where you are able to make predictions in p dimensions. Okay, so here we have 2 dimensions for p, which then forms a plane, and we're projecting onto there. But I don't know. The other one is easier to draw with only, but this almost feels trivial. But yeah, that's what we're doing. Okay. Are there any questions? Okay. You can always look up geometric interpretation of the least squares regression. You have other people trying to explain this as well, but it's the same kind of deal there. Yes, question.
Is there a reason why you want to cover this?
So I guess well, I don't know. It seems like it's a topic in classical regression that always gets covered. That you know, our book. I like our book, but it seems to focus more on just kind of the R commands, which is fine, and it also shows you kind of a bunch of these derivations here. And I know I didn't do any kind of derivations, but the idea is, I don't know, maybe presenting another possible interpretation that makes it, I don't know, I hope helpful to see, or maybe visualize how this the regression idea is working here. But yeah, I probably won't be testing you on this per se, but it's just kind of a different topic. I thought that multiple linear regression, I think, is ideal place to introduce this. So, okay, we'll end there. Have a good, safe weekend, and we'll see you guys on Monday.